Hello everyone, welcome to the lecture again. In the last lecture, we discussed the shear force and bending moment when the loading was concentrated. We saw that when the beam is subjected to a concentrated load only, in that case the shear force is constant between the load and the bending moment varies linearly. Today we are going to discuss the shear force and bending moment in the case of distributed load. So, the situation is following. Suppose I have a beam and let us say on this end we have a pin joint and over here we have some roller support. Let us say this is x axis and this one is y axis, and this beam is under some distributed load. So, let us say the load is like this. Let us say the load per unit length, which is called the loading intensity, that is W. So, W as a function of x, which is a continuous function, is a loading intensity. Okay. And let us say we want to analyze a section of this beam. Okay. So, let me consider a part of the beam, let us say between A and point B, and to analyze that let me take an infinitesimal part of the beam. Let us say this part is dx and from one end it is at a distance of x. Okay. Now, let us look at the free body diagram of this infinitesimal part dx. So, free body diagram of infinitesimal element dx. Okay. So, we have this part. So, this is dx, and on the left hand side let us follow the positive convention. So, we have the force B and the moment m, and on the right hand side we will have, let us say the force is acting downward, it is V plus dV and the bending moment is m plus dm. Okay. Now, this part will also have the load. So, the load will be load intensity W multiplied by the horizontal length, which is dx. So, therefore, the load will be W dx and it will act at a distance of x by 2. Okay. So, dx by 2 because the length is dx. So, therefore, this will be dx by 2 and also on the other side it will be dx by 2. Let us consider that this point is O for the analysis. Now, to find out the shear force V, we can balance the forces in the y direction. So, let us use summation Fy is equal to 0. So, we got V minus W dx minus V plus dV equal to 0. What does this mean? This means that, so V can get cancelled, we get W equal to minus dV over dx. Let us call this equation number 1. This implies that the load intensity, which is W, at any section of a beam is equal to the negative of the slope of the shear force, because V was the shear force. So, we have dV by dx. So, it is the slope of the shear force diagram at that section. Okay. Now, we can find out from here what is V just by integrating it. So, let us integrate this between the section A and B. Okay. So, let us integrate between the section A and B to find out what is V. So, we have integral x A to x B w dx equal to, so w dx equal to minus dv by dx equal to minus x A to x B dv by dx, and then we are integrating with respect to x. This gives you A to B w dx equal to minus Vb minus Va, and from here we can find out that the shear force at point B will be the shear force at point A minus w dx is the area of the W diagram. So, we have this load intensity, you find out what is the area of that, that will give you W dx integral. So, this on the left hand side we have area of W diagram between A and B. Let us call this equation number 2. In text we can say that the difference between the shear force at two sections of a beam is equal to the negative of the area under the load diagram between those two sections. Okay. So, now, so this is about the shear force. Let me again make the diagram of that infinitesimal part. So, we had this as dx, we assume that in this direction V is acting, the bending moment is like that, in this direction we have V plus dV and the moment is m plus dm, this is W dx acting at a distance of dx by 2 from the right, and we said that let us take this point O for the analysis. So, we got the forces, now let us find out the bending moment. Okay. And to find out the bending moment, let us take the moment about O. Okay. So, again the moment equation has to be balanced. So, let us take the moment about O and let us put it equal to 0. So, we have moment about O, V plus dV will not contribute. So, we have m plus dm plus W dx multiplied by the perpendicular distance which is dx by 2 equal to moment m plus force V multiplied by the perpendicular distance which is dx. Okay. Now, you can see here that m will get cancelled and this term W dx and dx by 2 it has dx twice. So, dx is small, therefore, this term will be even smaller. So, let us drop this term because dx is small, therefore, we are dropping this. So, we get dm equal to V dx or we get V equal to dm divided by dx. Let us call this equation number 3, and this equation implies that the shear force at any section is equal to the slope of the bending moment diagram at that section. Okay, because dm by dx is the slope of the bending moment diagram. Now, to find out what is the value of m, let us again integrate this between a and b. So, let us integrate between section a and b. So, we had v equal to dm by dx. So, x a to x b v dx equal to integral x a to x b dm by dx and dx. Okay. So, this gives you between a and b v dx equal to m b minus m a, or we can write down m b as m a plus the area of V diagram between A and B. Let us call this equation number 4, and we can again write it down in the text. This implies that the difference between the bending moment at two sections of a beam is equal to the area of the shear force diagram between these two sections. Okay. Now, from all this analysis, we can also see that in general, if the load diagram is a polynomial of degree, let us say m, then the shear force diagram will be a polynomial of degree m plus 1, and the bending moment diagram will be a polynomial of degree m plus 2, because we have this equation. So, V will be w dx, and if w is a polynomial of, let us say, m degree, in that case V, because that is the integral of that, it will be of the order of m plus 1, and similarly for the bending moment diagram, because that is the integral of V. Okay. Now, with this basic concept, let us now look at couple of examples. So, the first problem statement is following. A cantilever beam carries a triangular load and its intensity varies from 0 at the left end to 360 Newton per meter at the right end. In addition, a load of 1000 Newton upward act at the free end of the beam, and in the question it has asked you to derive the shear force and bending moment equations, and it has also asked you to draw the shear force and bending moment diagram. It is also given that you can neglect the weight of the beam. Okay. So, first of all, let us see here the load is a linear function of x. Okay. So, therefore, it is obvious that the shear force will be one order higher. So, that will be, it will depend upon the x square. Similarly, the bending moment will depend upon the x to the power cube. So, let us see that. Before we analyze this, first let us consider the free body diagram of the entire beam to find out the reaction forces. So, let us look at the free body diagram. Of the entire beam. Okay. So, we have point A, point B, this is our x axis, this one is y axis, and the loading is like this. Okay. Here we have an external force of 1000 Newton. Let us put reaction force By over here and bending moment Mb. Now, we can find out the area under the curve. So, that will give us the total loading. So, that will be, so first of all it is going to act. So, this is 12 meter from the right hand side, it is going to act at a distance of 1 by 3 of the base. So, this is 1 by 3 into 12 meter equal to 4 meter. So, this distance is going to be 4 meter. Now, how much is the loading intensity? So, load will be 1 by 2 into 12 into this is given. So, this is 360 Newton per meter. So, therefore, 1 by 2 into 12 into 360, and this will give you 2160 Newton. So, that much force is going to act downward. So, this completes the free body diagram of the entire beam. Now, let us use the force balance equation first to find out what is the reaction force at point B. Okay. So, let me call it RB. So, we have summation Fy equal to 0, this gives you Rb equal to 1160 Newton, because we have 1000 force acting upward and we have 2160 Newton force acting downward. So, therefore, Rb will be 2160 minus 1000, which is 1160 Newton. Now, to find out the moment, this Mb, let us take the moment about B. So, in that case the RB is not going to do anything because it is passing through point B. So, we have MB plus we have 2160 multiply by the perpendicular distance we have just calculated, it is 4 meter, equal to 1000 into 12. So, this gives you MB equal to 12,000 minus 4 into 2160, which is 8640, and this gives you MB equal to 3360 Newton meter. So, these are all the forces that are acting. Now, to find out the shear force and bending moment, let us draw a part of this beam. Now, note that because the loading intensity is continuous, the beam does not need to be divided into many segments. Okay? Only one expression of V and M will apply to the entire beam because it is a continuous loading and single loading. So, let us look at the free body diagram of the left hand part of this beam. So, let me just make it once again. So, this was the entire beam, let me make it here. So, we have our x axis and this is the part that we are interested in. So, therefore, it is like this. Let us say this is at a distance x, the end part is at a distance x from the left hand side. This is our y axis and here I have external loading of 1000 Newton, and here let us say that V is acting like this and M is going to act like that. Now, from a distance of x by 3 from the right side, the entire weight of this section is going to act and it will be 1 by 2 into x into this height. Now, this height I can find out using the equation y equal to mx, where m is the slope and this m I can find out from the entire beam. So, y is equal to m is 360 divided by 12 into x. So, therefore, y is equal to 30x. So, therefore, this is 30x equal to 15x square. Okay. Now, let us balance the forces to find out what is V. So, let us use summation Fy equal to 0. So, this gives you 1000 equal to V plus 15x square, and this gives you V is equal to 1000 minus 15x square. So, you can see that V varies as a function of x square because the loading is a linear function of x. Now, to find out the shear or the bending moment, so it will be summation m, let us take this point as C. So, let us take the moment about C. So, it will be m plus 15 x square into the perpendicular distance, which is x by 3 equal to 1000 into perpendicular distance is x. Note that V is not going to take part in this because we are taking the moment about C and V is passing through C. So, therefore, m will be 1000x minus 5 x to the power 3. Now, let us plot this V and m as a function of x. So, let us say this is x axis, this is V. So, you can see here that the plot of 1000 minus 15 x square, because of minus 15 x square it is going to decrease. So, therefore, it will go like that, and we can find out what is the maximum values and what is the minimum values. For the maximum value of V, let us put x equal to 0. So, for V max, let us put x equal to 0. This will give you V max equal to 1000. So, therefore, this is 1000. Now, for V equal to 0, let us find out what is the value of x. So, again let us use this equation, put V equal to 0. So, 0 equal to 1000 minus 15 x square. This will give you x equal to 8.165 meter. Therefore, this distance is 8.165. So, at this moment the shear force will be 0. Now, on the other hand, so let us say over here, let us find out what is its value. So, for that we know that here x is equal to 12 meter. So, therefore, again in this equation let us put x equal to 12. So, we will get V equal to 1000 minus 15 into 12 and this will give you minus 1160. So, therefore, this value will be minus 1160. So, this completes the shear force diagram. Now, let us look at the bending moment diagram. So, this is our x axis and because of x minus ax minus bx cube term. So, the plot will be like that. So, you can plot it and you can see it will look like this. Now, let us find out the various points on this plot. So, first of all we can see that from this equation at x equal to 0 my m is 0. Okay. So, therefore, this point is 0, this is m. Now, let us see what is the maximum value of m. For that we have to take this equation and differentiate this with respect to x, put that equal to 0, that will give you the maximum value of the point of m, and then you can find out what is the maximum value of m. So, let us do that. So, we have this equation, let us for maximum value of m, let us say dm by dx equal to 0. So, that will be 1000 minus 15 x square equal to 0. From here you can find out what is the value of x. So, x will be square root 1000 divided by 15 and it will come out to be 8.165 meter. So, therefore, this is also 8.165 meter, and at that we have the maximum value of m. To find out the maximum value of m, let us put this value of x in this equation. So, let us do that. So, we will have m is equal to 1000 into x, which is 8.165 minus 5 into x cube. So, 8.165 to the power 3, and this will give you 5443 Newton meter. So, therefore, this will be 5443 Newton meter. Now, I also know that at this point x is equal to 12. So, again in this equation I can put x equal to 12. So, let us put the value of x equal to 12 in this equation, and this will give you m equal to 1000 into 12 minus 5 into 12 into 12 into 12, and that will be 3360 Newton meter. So, therefore, this value will be 3360 Newton meter. So, this completes the question, and we have find out what is the bending moment and shear forces. Now, let me give you a homework problem, and the problem statement is following. So, this is a homework problem. Draw the shear and bending moment diagrams for the beam and loading shown, and determine the location and magnitude of the maximum bending moment. Okay. So, just to give you the hint, you can consider the free body diagram of the entire beam, and this will give you the reaction at A equal to 80 kilonewton, that will act upward. Similarly, the reaction force at C will be 40 kilonewton, and that will also act upward. You can find out the shear force at point B. So, shear force at point B will be minus 40 kilonewton. The shear force at C will also be minus 40 kilonewton. You can find out the bending moment. So, the bending moment at point D will be plus 160 kilonewton meter. Now, D is the point where in the bending moment will be 0. Okay. So, this is the point where bending moment will be 0. You can find out the bending moment at point P, it will be 120 kilonewton meter, and the bending moment at point C will be 0. The diagram will look like this. So, let me plot V. So, point D is the point where the shear force will be 0. So, let me just plot this. So, this is the point, let us call it D. Okay. Here the value will be 80 kilonewton, and then it will look like this. This will be minus 40 kilonewton, and this is the distance, let us say x, which comes out to be 4 meter, and the shear force diagram will be like that. So, it will attain a maxima at point D, and then it will be like this. So, from here to here it will be a straight line. So, here it will be 120 kilonewton meter, and here it will attain the maxima 160 kilonewton meter. So, this question you can try by yourself. So, with this let me stop here. Thank you.